Hi, thanks for joining me. Today I'm going to be proving that root 2 is irrational, and in classic JPy maths form, this is going to be a non-standard proof. I've already made a few non-standard proofs to, the irrationality of root 2 and things like that, so I'll leave links to those in the description below. But without much further ado, let's get stuck in. Okay, so as with most proofs of the irrationality of root 2, this is going to be a proof by contradiction. So we're going to start by assuming or supposing for contradiction that root 2 is equal to a over b, where a and b are positive integers. Then we're going to insist that a and b are co-prime, so their greatest common divisor is 1. They share no factors. Okay, and what this kind of subtly means is that if we could write root 2 as a tilde over b tilde, where a tilde and b tilde are positive integers, then because of this fact here, we must have that a tilde is bigger than or equal to a, and b tilde is bigger than or equal to b. Because if a tilde, say, was smaller than a, then that means, well, if you have a little think about it, that means that there's something cancelling on the numerator and denominator here to give us the a tilde. So then that means that that means that a and b must have a common factor, which we're supposing is not the case. Okay, so if we can find another way of writing root 2 as a ratio of two positive integers, those positive integers must satisfy that the numerator is bigger than a and the denominator is bigger than b. And the way we're going to arrive at our contradiction is to find some other way of writing root 2 as a fraction, where the number here, the numerator, is less than a and the denominator is less than b. Okay, and how we're going to start off is just by writing root 2, which we know is a over b. And then, well, also using the fact that, well, 1 is less than root 2 is less than 2. We know that root 2 lies between 1 and 2. So root 2 we know is just a over b. And then just multiplying this inequality gives us that b is less than a is less than 2b, like so. So a minus b then is positive, so in particular non-zero. So I can write this as a times a minus b divided by b times a minus b, like so. Then just expanding this numerator is equal to a squared minus ab divided by b a minus b, like so. But a squared, well, we know that if we square both sides here, we get that 2 is equal to a squared over b squared. So then bringing the b squared onto here, we get 2b squared equals a squared. So a squared, this guy here, is just 2b squared. So 2b squared minus ab is divided by a minus b, or sorry, b times a minus b. This guy is still a over b. But notice on the top we can factor out a b, and on the denominator we've already factored out a b, so those can cancel. So if we cancel this b with this b and make that 1, we've now got that a divided by b is equal to 2b minus a divided by a minus b. Now I claim that this is a contradiction. Let me clean up the whiteboard and I'll quickly explain why. Okay, so we just showed that a over b is equal to 2b minus a over a minus b, and we have that a is bigger than b and 2b is bigger than a, and that came from the inequality that 1 is less than root 2 is less than 2. Okay, now what we notice is that 2b minus a from this inequality here is positive, so the numerator is positive, and a minus b from this inequality here is also positive. So we've got a positive integer divided by a positive integer, and that equals this root 2 term here. But now I claim that 2b minus a is less than a, and a minus b is less than b, which contradicts those inequalities we had before, and then that will mean that we've kind of found our contradiction. So I claim that 2b minus a is less than a. Well, this is clearly true if and only if 2b is less than 2a, which is clearly only true if and only if b is less than a, which we know is true from that inequality there. And in fact, this is all we need to do, but just for sort of completeness sake, let me just show that a minus b is also less than b. So a minus b is less than b, and this is true if and only if 2b is bigger than a, and that comes directly from that inequality there. Oopsie daisy. Like you said. So we've arrived at our contradiction. We've shown that if we could write root 2 is a over b, then we can kind of by infinite descent, we can always cancel numbers from the top and bottom to make that the numbers in the numerator and denominator smaller and smaller. But because they're positive integers, that you just can't do that. They're bounded from below, and you can't keep taking away from them. So this proves this is our contradiction, and hence that means that our original assumption was false, and thus root 2 is irrational. I hope that's all made sense. I thank you for watching. I'll catch you in the next one. Have a great day.